Section 7.4 is the last section of identities in Chapter 7. These are the double angle and half angle identities. We're going to start with the double angle identities. If you want the proof for any of these double angle identities, take a look at page 448 in your textbook. I'm guessing none of you do, and that's okay. I just want to make it available to you so you're not just wondering how in the world I come up with these identities. So we're going to start. We've got actually 5 double angle identities that involve just 3 of the trig functions. So sine, cosine, and tangent. Sine and tangent only have 1, but the cosine you can write it in 3 different ways. Okay, so the sine of 2 theta becomes 2 cosine of theta times the sine of theta. That would be the double angle identity for sine. For cosine, there are 3 different ways you can write this. You can write this as cosine squared of theta minus the sine squared of theta, or you could write it as 2 cosine squared of theta minus 1, or you could write it as 1 minus 2 sine squared of theta. Both of these two right here are based off of this one, come off of manipulating this one in terms of using the Pythagorean identity where it says sine squared plus cosine squared equals 1, and just kind of manipulating and combining things to make it fit what we want. And sometimes it is beneficial to find the cosine of 2 theta by using the sine of an angle, and I'll show you how to do that here in just a little bit. The tangent of 2 theta is equal to 2 tangent of theta over 1 minus the tangent squared of theta. So those are our 5 double angle identities. Let's go ahead and try using them to solve and find exact values. So if the sine of theta is equal to, that's equal to 3/4, and theta has its terminal side in quadrant 1, find the exact value of each function. And we're going to start with the sine of 2 theta. So the sine of 2 theta, if we're going to use that identity, let me scroll back up there, sine of 2 theta is equal to 2 cosine theta sine theta. Okay, so this is equal to 2 cosine theta times the sine of theta. We have a problem though. We don't know the cosine of theta. So what we need to do first is we need to actually find the cosine of theta. And I'll do that in purple. I'm going to just jot this off to the side. Find the cosine of theta. And what we're going to do is we're going to use that Pythagorean identity that I mentioned earlier. Sine squared plus cosine squared is equal to 1. We know the sine. We can square that. We can say 3/4 squared plus cosine squared is equal to 1. I'll move the 3/4 squared over as well as square it. So 1 minus 9/16. So then the cosine squared is equal to, 16/16 minus 9/16 would be 7/16. And then we would need to square root both sides. So the cosine is equal to plus or minus square root of 7/4. Because remember, square roots have 2 answers. When we're solving with square roots, we need 2 answers. However, we have this terminal side in quadrant 1. If we're talking quadrant 1 and we're talking cosine, if we use the plus, plus, minus, minus rule, cosine in quadrant 1 is positive. So we can really just eliminate this plus or minus and just assume that the cosine is positive. So if we're actually going to find the sine of 2 theta, now that we know the cosine, we can just plug everything in. We can say it's equal to, I'll go 2/1, times the cosine, which is the square root of 7/4, times the sine, which we already knew that was given to us, 3/4. The denominator, that's pretty easy. That's going to be 16. The numerator, we can multiply 2 and 3. We can't really do anything with the 7, so we can make it 6 square root of 7/16, which we can then simplify 6/16 down into 3/8, and we still have the square root of 7. So I would say the sine of 2 theta is equal to 3 square root of 7/8. Let's try another one. We got the same setup. We still have a sine being 3/4. The angle is still in quadrant 1, but now we're going to find the cosine of 2 theta. I think it's going to be beneficial to use this one to find our cosine of 2 theta. That doesn't mean we have to use that one. Because we know the cosine already, we found that already, we could use any one of these 3. But I think just because we were already given the sine, and this identity only uses the sign, I think it makes most sense to use that one. Does that mean you have to use that one? By all means, no. But just understand that since this one only had sign, we were given sign, to me it makes sense to use that one. So we'll say that cosine of 2 theta is equal to, it's 1 minus 2 sine squared of theta. Okay, so this will be 1 minus 2 times the sine was 3/4, so we'll go 3/4, and then we will square that. Okay, so this is 1 minus, we'll go 2 over 1, 3 squared is 9, 4 squared is 16. 16, there it is. Okay, so this will be 1 minus 2 times 9 is 18. 1 times 16 is 16. We'll need a common denominator here, so 16 over 16 for that one. Minus 18 over 16 is going to be negative 2 over 16, which that simplifies down into negative 1/8. I do have one more example. We just did sine, we did sine first, we did cosine next, so it only makes sense then that we finish with tangent. So we're looking for the tangent of 2 theta. We still have the same setup. We still know that the sine is equal to 3/4, and we know that we are in quadrant 1. Okay, so we need to find the tangent of 2 theta. So the tangent of 2 theta is equal to, if we go back to our identity, that is 2 tangent of theta over 1 minus the tangent squared of theta. Let me extend that fraction bar just a little bit. Before we can actually figure this out, we might need to know what the tangent is. We can use another one of those Pythagorean identities that says the tangent is equal to the sine over the cosine, and that'll help us find the tangent because we already know the sine and we already know the cosine. We did that earlier. We know the cosine is here, the sine was given to us, so let's go ahead and figure out what the tangent is. Okay, so the tangent was equal to the sine, which was 3/4, over the cosine, which was the square root of 7 over 4. That's a really bad 4. Now, if we're dividing fractions, 3/4 divided by 7, square root of 7 over 4, we can make this 3/4 times the reciprocal, 4 over the square root of 7, which gives me 3 over the square root of 7. And then to pull the square root out of the denominator, we can say that it's equal to 3 square root of 7 over 7. All right, now that we have the tangent of theta is equal to 3 square root of 7 over 7, now we can actually plug in that value into here. Actually, it would be here, and then we can find what the tangent of 2 theta is actually equal to. So this is equal to 2 times, this will be 3 square root of 7 over 7 over 1 minus, and then again, 3 square root of 7 over 7 squared. All right, let's try to clean some of this up here. The numerator becomes 6 square root of 7 over 7. The denominator becomes 1 minus, let's see, 3 square root of 7, I'm going to do this off to the side here, 3 square root of 7 times 3 square root of 7 for 3 square root of 7 squared becomes, let's see, 3 times 3 is 9, and then square root of 7 times square root of 7 is 7, so that's 63. So my numerator on this little teeny tiny fraction here, after we square it, is going to be 63. My denominator, just 7 squared, is 49. Okay, so I still have 6 square root of 7 over 7 on top. The bottom becomes, let's see, again, I would need a common denominator, so 49 over 49. So 49 minus 63 is negative 14 over 49. If we want, we could simplify that right away. We can make this 6 square root of 7 over 7 over, let's see, 14 and 49 are both divisible by 7, so we can make that negative 2/7. Negative 2 over 7, because negative 14 divided by 7 is negative 2, and 49 divided by 7 is 7. Now we can go ahead and multiply by the reciprocal, so we have 6 square root of 7 over 7 times the reciprocal, so negative 7 over 2. The 7s cancel out, not the negative, just the 7s. The 6 and the 2 can kind of simplify. They're both divisible by 2, so that's a 1. These were both 1s. And 6 divided by 2 is 3. So really what I'm left with now, it looks like 3 square root of 7 times negative 1 is going to be negative 3 square root of 7. And 1 times 1 on the denominator, well, that's just 1. So I'd say that right there is our answer, negative 3 square root of 7. So there's a little introduction on double angle identities, one using sine, one using cosine, one using tangent. Hopefully that becomes a little bit useful once you start working on practice problems. What I want to move to now, whoops, and I never scrolled that back, is half angle identities, because we talked about double angles and the title also included half angle identities. So half angle identities, again, there's only 3 of them, sine, cosine, tangent. I just want to lay them out for you, and then we'll kind of go through a couple of examples to kind of solidify this. So the sine of theta over 2 is equal to, we're going to start with plus or minus, then it's going to be one big square root, and it's equal to 1 minus the cosine over 2. The cosine of theta over 2, plus or minus, square root of 1 plus cosine of theta, I should put theta there, cosine of theta over 2. And tangent is a little bit messy. It again is plus or minus square root of 1 minus the cosine of theta over 1 plus the cosine of theta. Just a little side note here, 1 plus, actually we'll just do this, the cosine of theta cannot be equal to -1, because if cosine of theta was equal to -1, 1 plus -1 gives you 0, and then you got a whole mess. Okay, so we have actually 6 identities, one positive, one negative for each one. The question becomes, how do you know which one to use? And you're going to use the plus plus minus minus rule. Use plus plus minus minus to determine, DET, determine the signs, plus or minus, okay? How would this be useful is probably your next question. Why would I need to know the half angle identities? Well, if I asked you for the sine of 15 degrees, we don't really know 15 degrees, but what we do know is we could double this, double our angle to make it 30 degrees, and then we could say our angle, our theta, is 30, and we actually know the cosine of 30. Or, for example, if I wanted you to use a half angle identity to find the exact value of the cosine of pi over 8. Pi over 8. I don't know pi over 8, but what I do know is if I double this, that would be pi over 4, and I do know some values of pi over 4. Okay, so before we just go plugging things in, we might need to figure out what our angle measure is. Okay, how we're going to do that is we're basically going to take this angle and double it, because to figure out our theta, we originally were dividing it by 2. So if pi over 8 is equal to theta over 2, then it kind of makes sense then if we wanted to multiply both sides by 2, that would give theta by itself. These will go away. Theta would be equal to pi over 4, 2 pi over 8, which then simplifies into pi over 4. So what we can do is we can say that the cosine of pi over 8 is equal to the cosine of pi over 4 over 2. And then we can actually figure out our values, because in all of these identities, this angle that we use goes here. So in this case, pi over 4 is my angle that would go in for theta. So let me show you how this works. So cosine of pi over 8 is equal to the cosine of pi over 4 over 2. I'm going to use the cosine identity, obviously. Now, pi over 8, we'll come back to the sines in a minute. We'll just skip that part for now. So we'll say the cosine of pi over 8 is equal to the cosine of pi over 4 over 2. And this, again, this is my theta right here. So it's going to be plus or minus square root of, let me go back to the identity. We're talking cosine, so it's 1 plus the cosine of the angle. So it's going to be 1 plus the cosine of my theta, which is pi over 4, all over 2. Now, we can work this down and evaluate it to get a singular exact answer. Cosine of pi over 4, so equals plus or minus square root 1 plus cosine of pi over 4. That's on the unit circle. Cosine of pi over 4 is square root of 2 over 2, and that's still all over 2. I should probably adjust this square root, this radical symbol, so that the entire fraction is underneath the square root. Let's see. We should combine the numerators here. That'd be 2 over 2 plus square root of 2 over 2. So this becomes plus or minus, so 2 over 2 plus square root 2 over 2, all over 2. Lots of 2's in this example. So I'm just going to kind of work back over here to the left. So the numerators I can combine. So it becomes big square root plus or minus 2 plus square root of 2 all over 2 all over 2 again. And we can keep going. Now, if I'm taking something, in this case 2 plus the square root of 2, and I divide it in half, and then I divide it in half again, because that's really what this is saying. If you divide something in half and then in half again, what you've done is divided into fourths. So this becomes plus or minus square root of 2 plus the square root of 2 all over 4. Again, if you want to make this 2 over 1 and multiply by its reciprocal, you're going to get the same thing at the very end. But you don't necessarily need to. If you're dividing something by a number and then you divide it by something else, you can just multiply these. Like if this was over 3 and then over 2, this would become 6. But since it was 2 and 2, we've got 4, which actually works out very, very well because we can make this plus or minus square root of 2 plus the square root of 2 over the square root of 4. We can use the quotient property of square roots or radicals to split this square root into one big ugly fraction into maybe something that's a little more manageable. The reason we do that is because the square root of 4 is a great number. We don't want any fractions under the square root, and we don't want any square roots under the denominator. And that's a good thing because we're not going to have that. So our answer then is going to be plus or minus square root of 2 plus square root of 2 all over square root of 4 was 2. Now the question becomes, is this a positive or a negative? Well, pi over 8 is in the first quadrant. So if it's in quadrant 1 and it's cosine, anything in quadrant 1, our trig values are going to be positive. So you could say positive, or you wouldn't even need to write anything at all. You could just leave it blank. So you could say the cosine of pi over 8 is equal to this whole mess. Let's try one more here. Tangent of 15 degrees. Again, 15 degrees is not a number that we have on our table. It's not something that we normally think of on the unit circle. So we need to maybe use some identities. In this case, we're going to use a half angle identity to actually find the exact value of the tangent of 15 degrees. So if we think about double angle, we could say 15 is equal to our original theta over 2, which means if we use just some simple single-step algebra solving skills, we could find that theta is equal to 30 degrees. And that's going to come in handy when we use our identities. Tangent of 15 is in quadrant 1. So we'll say quadrant 1, which means we are using the positive square roots. We don't need to worry about the plus or minus. So let's go ahead and find this out. So we can say the tangent of 15 is equal to, we're going to have big square root, 1 minus the cosine of our theta. Our theta is 30 degrees, so it's going to be cosine of 30 over 1 minus the sine of 30. Not sine, I apologize. It's not even minus. I don't know what I'm thinking. It's 1 plus the cosine of 30 degrees. That's my bad. Mental lapse there, my bad. All right, so 1 minus the cosine of 30, so we still have big square root. 1 minus cosine of 30, that comes from the unit circle. That's the square root of 3 over 2 over, get rid of some of that extra square root, 1 plus, and again, cosine of 30, same thing, square root of 3 over 2. And I apologize for kind of the bad handwriting. I'm trying to write smaller so it all fits. The numerator of our big fraction and the denominator of our big fraction both should probably be combined. So how I'm going to do that, I'm just going to make this 2 over 2 minus square root of 3 over 2 and 2 over 2 plus the square root of 3 over 2. And what's going to happen when we combine all that together is we're going to have 2 plus the square root of 3 over 2 over 2 minus the square root of 3 over 2. And again, I'll get rid of some of this extra square root. There we go. And then once again, we can have that whole dividing fractions. That's our cry. Flip one over and multiply. So we can make this square root of 2 plus the square root of 3 over 2 times it's the reciprocal of the denominator. So 2 over 2 minus the square root of 3. Something nice happens here. These cancel each other away. So what we're left with then is the square root of 2 plus the square root of 3 over 2 minus the square root of 3. That's a 2. Okay? Well, we still have fractions under the square root, and we still have square roots in the bottom. So we still have some work here to be done. Just like in section 7.3, where we had an example of a square root in the bottom of our fraction. To get rid of it, we need to multiply both the numerator and denominator by the conjugate of the denominator. So what this looks like, I'm going to extend this square root Actually, I'm going to do this in a different color. I'm going to do it in blue, something that really stands out. So we're going to go times, and it's going to be not the reciprocal, but the conjugate of this. It becomes 2 plus the square root of 3. So the denominator becomes 2 plus the square root of 3 times over 2 plus the square root of 3. Okay? A couple of different ways you can do this. I'm going to show you both ways. One way might seem a little easier than the first. The way the book shows this, if you were to look in the book, I believe this example is in the book. If not, I can show you the steps. How this works, I'm going to just split this screen right down the middle in half. Okay, so the left side I'm going to do the way the book would do. And what this looks like is this is equal to the numerator. Let's see, I'm going to make a big square root. The numerator just becomes 2 plus the square root of 3 squared, because we're taking this times itself, 2 plus the square root of 3 squared. The denominator, we're going to have to FOIL out. So this is going to become, so let's see, 2 times 2 is 4. 2 times the square root of 3 is just 2 square root of 3. Negative square root of 3 times 2 is going to be negative 2 square root of 3. And that's going to work out nicely. And then negative square root of 3 times positive square root of 3 becomes negative square root of 9. Okay, so this becomes square root of 2 plus square root of 3 squared over, let's see, this is a 3. These cancel each other away, so we got 4 minus 3, which is just 1, and that works out really well. So really what this is the square root of 2 plus the square root of 3 squared, and that old inverse operation, the square root and the square cancel each other out, so this cancels that, so what we're really left with is 2 plus the square root of 3. Now, when I solved this on my own, that was not my original plan of attack, and I did not get that same answer. However, when you evaluate them or plug them into the calculator, you do get the same value whether you do it this way or whether you do it the way that might stand out for you a little more, where the denominator is actually going to work the same way. We're going to have to FOIL the denominator, but if you FOIL the numerator, you're not going to get something that looks like this at the end. It's going to look a little more complicated, but when you type it into the calculator to evaluate, you do get the same answer for both. Okay? So, how I did this originally, I know the denominator works out the same way. I know it's going to be 4 plus 2 square root of 3 minus 2 square root of 3 minus 3. That all happens the same way. But I actually FOILed the numerator out as well up here. Okay? So that's going to give me 4. Let's see, 2 times the square root of 3 is 2 square root of 3. The square root of 3 times 2 is another 2 square root of 3. And square root of 3 times the square root of 3 is the square root of 9, which I know that's 3. And I can combine 4 plus 3. That gives me 7. So I'm going to have the square root of 7, and then 2 square root of 3 plus 2 square root of 3 is 4 square root of 3 over, and once again, that cancels with that. 4 minus 3 is 1, and if it's over 1, we really don't need to worry about it. We can just say it's equal to the square root of 7 plus 4 square root of 3. Either way, if you type this into the calculator or this one, what you're going to get is, shouldn't do equals, it's roughly 3.73.